Imagine a ripple, not on water, not in air, but in the very fabric of space and time itself. A tremor traveling across the cosmos, born from the collision of black holes billions of light years away. And somehow, that ripple reaches us, subtly stretching and squeezing the Earth by less than the width of an atom. This is not science fiction. This is gravitational wave physics, one of the most extraordinary discoveries in modern science. Welcome to the Learning Studio, and in today's episode from our physics playlist, we'll explore gravitational waves and multimessenger astronomy, where Einstein's theory meets artificial intelligence, and where data, not just light, reveals the heartbeat of the universe. You can watch the entire physics playlist by clicking the link in the description below. This topic belongs to our new section Space, Time, and Advanced Technologies, where we study how the universe speaks to us through waves, particles, and the power of computation. The story begins, Einstein's whisper across a century. In 1916, Albert Einstein predicted something extraordinary through his general theory of relativity. That massive objects like stars or black holes could distort space-time, and when they accelerate violently, these distortions would radiate outward as gravitational waves. For nearly 100 years, these waves remained a mathematical whisper, too faint for any instrument to detect. Then, in 2015, a century after Einstein's prediction, the LIGO observatory recorded the first ever gravitational wave signal. Two black holes, each about 30 times the mass of the Sun, collided 1.3 billion light-years away, and for a fraction of a second, they shook the universe. That tiny vibration, smaller than a proton, was detected here on Earth, a scientific triumph that opened a new sense for humanity. Just as Galileo's telescope opened our eyes to the cosmos, gravitational waves opened our ears. Listening to the universe, beyond light. Until recently, all astronomy was based on light, visible, infrared, radio, or X-rays. But gravitational waves let us listen to cosmic events that emit no light at all, collisions of black holes, neutron stars, and even the earliest echoes of the Big Bang. This new field, multi-messenger astronomy, combines data from multiple cosmic messengers. Gravitational waves, electromagnetic radiation, neutrinos, and even cosmic rays. Together, they provide a richer, multi-dimensional picture of the universe. It's like switching from a silent movie to full 3D sound and color. Every signal adds a new layer of cosmic truth. Where AI enters the cosmos. But detecting gravitational waves is no simple task. The signals are incredibly faint, hidden within mountains of noise from earthquakes, traffic, and even quantum fluctuations in the detectors themselves. This is where artificial intelligence and machine learning play a starring role. AI models trained on simulated waveforms can instantly recognize gravitational wave signals in noisy data, distinguish true cosmic events from false alarms, and predict the physical properties, like mass, spin, and distance, of merging black holes or neutron stars. Deep learning algorithms like convolutional neural networks, CNNs, now scan through petabytes of LIGO and Virgo data faster than human scientists ever could, enabling near real-time alerts for astronomers around the world. When a gravitational wave passes, AI helps identify it, cross-reference it with telescopes, and coordinate global observation efforts, all in seconds. The symphony of the universe, when waves meet light. A milestone came in 2017, when both gravitational waves and light from the same event were observed for the first time. Two neutron stars collided in a distant galaxy, and detectors caught the gravitational waves, while telescopes captured the gamma-ray burst that followed. This cosmic duet, waves and light, confirmed long-standing theories about where heavy elements like gold and platinum are born. In other words, the atoms in your jewelry, your computer, and even your blood may have been forged in the violent merger of neutron stars billions of years ago. Multimessenger astronomy revealed not just how the universe works, but also how we came to exist. The future, smarter, faster, and deeper into the cosmos. The future of gravitational wave physics lies in data, precision, and machine intelligence. Next-generation detectors, like LISA, Laser Interferometer Space Antenna, will operate in space, sensitive enough to detect supermassive black hole mergers and even signals from the early universe. Meanwhile, AI models are evolving into real-time cosmic interpreters, capable of simulating, predicting, and classifying events across the entire sky. They'll not only detect what's happening but also forecast where and when the next cosmic collision might occur. We're moving toward a future where AI doesn't just analyze the universe, it helps us listen to it in ways we never could before. Why it matters. Gravitational waves remind us that the universe is not silent, it vibrates, sings, and communicates through the rhythm of space-time itself. And with machine learning, we now have the ears to hear it. This field doesn't just expand our knowledge of astrophysics, it redefines what it means to observe reality. It's the perfect union of physics, computation, and curiosity, a dialogue between the cosmos and consciousness. This is the Learning Studio, and this was our episode on gravitational waves and multi-messenger astronomy. If you loved exploring the symphony of the universe with us, don't forget to like, subscribe, and check out our physics playlist linked below. In our next episode, we'll journey into cosmological simulations and AI in astrophysics, how scientists are recreating the universe inside supercomputers. Because here at the Learning Studio, we believe, when the universe speaks, physics helps us understand its language.